Hello, am I audible? Hello everyone. This week we are going to solve problems on rotational motion. Last week, not exactly last week, 2 days ago, we solved the problem based on the kinematics. We saw that how to solve problem where the acceleration is constant, and in those cases we have to just use the three equations that we have derived from the very general relation. So the relation that we have used in the previous class mostly is the expression of velocity, which is the rate of change of displacement vector in time, and the relation of acceleration, which is the rate of change of velocity in time. And based on this relation, we actually derive three equations. So these three equations valid only when the acceleration is constant. And if acceleration is not constant, then we have to use this general equation. So anyway, we can use this general equation for all the cases. For the constant acceleration cases, mostly the problem reduced to this three set of equation. But if the acceleration is not constant, we saw that using this relation, differentiating and integrating in time, can give us the required result. So this is mostly in the Cartesian coordinate. Then we move to the curvilinear coordinate, and we saw that how to solve for velocity and acceleration. So the concept was same. We still use the same equation for the curvilinear coordinate, but we saw that in the curvilinear coordinate, acceleration doesn't always due to the change in velocity, but also due to the change in the direction of the particle, or change in the direction of motion of the particle. So just to revise this once again, because next we are going to solve problem based on the polar coordinate and then in the rotational motion. So it will be useful once again if we revise it whatever we have done in the last class. So let's say this is my point A, and it is the initial point, and this is point A dash. This angle is d beta, and this is the radius of curvature rho. So in the curvilinear coordinates, we are interested in two direction. One is the normal direction, and another is the tangential direction. And this is the change in position from A to A dash, which is ds, and this can be written as rho db beta. So my change in position will be rho d beta. Now if I assume that my radius of curvature is independent of time, then if I take the derivative of this equation in time, I will get ds by dt rho d beta by dt, and this ds by dt is my velocity. So this is v ds by dt rho d beta by dt, and I can write this as rho beta dot. So dot means I am taking derivative of that quantity with respect to time. So here this velocity is actually the velocity component which is in the tangential direction. So this can be written as rho beta dot et. Right? If I take the time derivative of this expression, I will get acceleration, which is rho, sorry, right? So here v and et both depends on time. So if I differentiate this, I will get v et dot plus v dot et. So this is my acceleration. So here the first component is due to the change of the direction of the tangential direction. So the acceleration induced due to the change in the tangential direction, and this component uh, contribute due to the change in the magnitude of velocity. So in order to understand this E dot t quantity, let we have a direction et, and it actually gets changed to et dash, and this is my change, which is d et, and this is the angle d beta, right? So this, you can see, this is the direction of et, and this is the direction of en, which is the normal component. This is the tangential component, and you can see this change in the direction et, change in the tangential component, is along normal direction en. So I can write the vector d et, it is in the normal direction with a magnitude of d beta, because this d beta will describe the magnitude of this d et. So if this d beta is very large, which means my d et is large, and if d beta is very small, which means this d eta is very small. So the magnitude is defined by this angle, which is d beta, and it has the direction en. So this is my en direction, and this is my tangential direction, et direction. So en is the normal direction and et is the tangential direction, and you can see this d eta is in the normal direction. So if I take the time derivative of this, I will get et dot equals b dot en. So I can use this relation here. So my acceleration will be and instead of v, I can use this relation rho b beta dot. So if I use this v equal rho b dot, then I will get here v square by rho in the normal direction and v dot in the tangential direction. This can still be modified into rho beta dot square or vb beta dot. So this is my normal component of acceleration, and this is my tangential component of acceleration. So then we use this relation of acceleration and this relation of velocity in the problems. We solve few problems based on the curvilinear coordinate. Now you can extend this concept to the polar coordinate. So in the polar coordinate, you will have a direction r and theta. So basically, just like you have described the change in the direction of change in the tangential unit vector, and we found that the change in the tangential unit vector is in the normal direction and it has the magnitude of d beta. Similarly, in the polar coordinate, you will have two direction. So this is radial direction and this is change in the radial direction. And this is theta direction and this is change in the theta direction. And you can see that the change in the radial direction and this angle is d theta. So this change in the radial direction is in the theta direction with the magnitude of d theta. It's a similar concept that we are applying, and the change in the theta direction is in the radial direction with the magnitude of again d theta. And as usual, as we take the time derivative, once again here we can write ER dot equals theta dot E theta and E theta dot equals theta dot ER. And based on this we can actually derive the velocity component in the polar coordinate. So it is actually V R dot ER plus R theta dot E theta. So this is my velocity component, and if you want to write the acceleration vector, then it will be acceleration rate of change of velocity. Then you have to take the derivative of this component and this component, and all is depend on time. So it will be R double dot ER plus R dot ER dot. Then you will have R dot theta dot E theta, then R theta double dot E theta, then R theta dot E theta dot. So here in the place of E theta dot and ER dot you can use these relations. So when you use this, you will have the expression of acceleration in the polar coordinate as R double dot minus R theta dot square ER. This is the radial component of acceleration, and R theta double dot plus 2R dot theta dot. This is the theta component of acceleration. So in the problem of polar coordinate, we will be using the same formula to calculate the acceleration. So in most of the problem, we need to calculate the magnitude of the acceleration vector, which can be given by this. In the previous class, we solved in the Cartesian coordinate, where the magnitude of acceleration given by ax square plus ay square under roots. So in order to calculate the
Himanshu, the last three classes did not happen, no?
so I took one class on Saturday. So
This Saturday.
yes.
But they had sent an mail saying that it was cancelled.
No, the again one mail they sent which says that the class is on Saturday, Monday, Wednesday.
I did not get it. I got the one that said it was cancelled, and the one that said Monday is there.
Oh, okay, okay.
Did anyone attend that day?
No, no, nobody attend.
I thought so because the mail did not come. Otherwise, I would have attended that day.
Okay. I mean, it was the same. So I actually put link to the previous semester class. So it was the same question. So still
Okay.
today also it was the same question only.
Okay, no. Previous when in the sense ki last time when you attend, it's the same thing. Is
Yeah,
what?
yeah.
Okay.
So these are my acceleration, and this is the expression of velocity for the polar coordinate. So let's solve few problem based on that. So basically in this kind of a problem, it's a formula based question. So in each of the problem you need to identify r double dot, theta dot and theta double dot, and just substitute in this equation. So it's a pretty it will be pretty straightforward problems. So let's solve this one. So here we have a radar gun at O rotates with angular velocity theta dot 0.1 rad per second and angular acceleration of theta double dot 0.025 rad per second square at an instant theta equals 45. As it follows the motion of the car traveling along the circular road having a radius of r 200 meter. Determine the magnitude of velocity and acceleration. So in order to determine the magnitude of velocity, it is given as vr square plus v theta square, and acceleration will be ar square plus a theta square. So basically we need to find the component, radial and theta component of velocity and acceleration. So the velocity vector is r dot er plus r theta dot a theta dot. So this is my radial component and this is my theta component, and acceleration vector is r double dot minus r theta dot square plus r theta double dot plus 2r dot theta dot. So this is the radial component of acceleration and this is theta component. So from the question itself you can actually write down various quantities like theta dot is 0.1, theta is 45, theta double dot is 0.025 rad per second square, r is 200 meter, and you can see the r is the constant. So if you take the time derivative of r, it will be 0, and r double dot will be 0 also because r is a constant here. So now if you plug this information here in the above expressions, you can see that this component will vanish because r dot is 0, and this is non-zero solution because r is 200 and theta dot is 0.1. So my v theta is r theta dot, r is 200 and theta dot is 0.1, so it's 20 meter per second. Similarly in the acceleration, this will vanish because r double dot is 0 here, and this is actually r is 200 and theta dot is 0.1. So this will be 2 meter per second square. Similarly this is non-zero because theta double dot is non-zero, and this will be 0 because r dot is 0 here. So r theta double dot is 200 multiplied by 0.025. So r theta double dot is 5 meter per second square. So your a theta will be r theta double dot, which is 5, and ar is minus 2 meter per second square. So your magnitude of acceleration will be just root 29 meter per second square, and the magnitude of velocity is 20 because my vr is 0, this will be vanish, so my v will be v theta square, which is v equals v theta. So in that case this will be v 20 meter per second. the magnitude of v, and this will be the magnitude of acceleration. So you can see that in this question it is the application straight of this formula. So we just use this acceleration formula and this velocity component. So you only thing that you need to ensure that to identify r double dot, theta double dot, r dot and theta dot, and once you identify that, you can just plug directly into the formula to calculate the magnitudes. So here we have given r, which is equals to 200 meter, and it was a constant which give r dot and r double dot 0. So let's solve one more problem, and here r is given as 0.4 theta, which means if you take the time derivative of r dot will not be 0. It's a similar problem, just different in how you are defining the r. So here the slotted link is pinned at O, and as a result of the constant angular velocity theta dot, it drives the pack P for a short distance according to r, which is 0.4 theta, where theta is in radians. Determine the velocity and acceleration of the particle when r is 0.5. So here r is 0.5 meter, and r is also varies as 0.4 theta. Theta dot is 3 rad per second. So theta dot is a constant, which means if you take the time derivative of theta dot, it will be 0. And if you take the time derivative of r, it will be r dot 0.4 theta dot. And you already know theta dot, which is 3. So your r dot will be 0.4 multiplied by 3. So r dot will be 1.2 meter per second. So in order to calculate so you can calculate theta also. So here you have r 0.4 theta, r is 0.5, so theta will be 0.5 by 0.4, which is 1.25 radian. So this is the theta. So once again we just use this expression. So my
Your mic is on mute, Himanshu. Yes, I think so.
hello.
And now I can hear.
Sure. So this is my r dot. So my VR is r dot, which is 1.2.
Is this dynamic? What is the name of this topic?
This is kinematics, rotational motion,
Okay, thanks.
and v theta is r theta dot. So theta dot is 3 and r is 0.5. This will be 1.5 meter per second. Then my r double dot is, so if I again differentiate this expression, I will have r double dot equals 0.4 theta double dot, and my theta double dot is 0, which and therefore my r double dot is 0. So this term will be 0 here. So my AR will be minus r theta dot square. R is 0.5 and theta dot is 3. Therefore AR will be minus 4.5 meter per second square, and A theta is r theta double dot plus 2r dot theta dot. So my theta dot is 0, sorry, theta double dot is 0, so this will be 0. So this is 2r dot theta dot. So my A theta is 2, r dot is 1.2, and theta dot is 3. So this is 7.2 meter per second square. So my magnitude will be 1.2 square plus 1.5 square. So this is my magnitude of velocity, and for acceleration it is minus 4.5 plus 7.2. So acceleration magnitude is 8.5 meter per second square. So as you can see that in this problem also we have used these relation directly. We just identify r dot, r double dot from this expression, and the remaining terms we actually got in the question itself. So in the previous question my r was constant, which, and therefore my r dot and r double dot was 0, but here r is given as a function of theta, and when you take the time derivative and derivative twice, you will have r dot which is 1.2 and r double dot as 0. So this was the only minor difference in this question, and in the both the question you actually use the same expression, identify r dot, theta dot and other quantities to find the component of velocity and acceleration. So any doubt until now?
No, I have not studied this topic, so I don't think I'll be having any doubts. I can just continue with the syllabus.
Okay, so this was the topic for the previous week. So now I am going to start the other topic this week.
Which is the topic?
So now it's a rotational motion. Basically, in this topic, we will study the rotational motion and the relative velocity in the rotational motion.
But the concepts are still based off kinematics and.
Yeah, yeah, it's the kinematics. From yes, previous lecture, it is now only kinematics.
Okay. I'll just listen because I have not studied that. So I'll understand most things.
Okay, so yeah,
Are these things easy, Himanshu? Like exam is in a month, so I don't know if And kinematics I've never done. So kinematics and the static friction. From static friction onwards until the end, is it doable?
Yeah,
The
yeah, it can be doable. Just need to. So basically, in the previous class, we study the velocity and acceleration concept for a moving body. So
okay.
basically, it was in the Cartesian coordinate mostly. So we already know the simple relation of velocity, which is the rate of change of displacement, and
Hmm.
acceleration, which is the rate of change of velocity in time. So we
Yeah.
use this concept, this expression to calculate position. So there are three in the kinematics. There are three quantities: displacement, velocity, and acceleration. And what happens in the kinematics that if you have given any of these three quantities, you have to find other quantities from these three itself. So for example, you have given the acceleration, then you can may have to find velocity and displacement. If you have given the displacement, then you may have to find velocity and acceleration. And that you need to find using these relations. So for
Okay.
example, let's say in the first question we solve where we have given the velocity expression as a function of time, and we
Hmm.
need to calculate distance, velocity and acceleration at
Need to differentiate v to get acceleration here.
yeah at time equal 3 seconds. So since we have given the velocity expression as a function of time, you just need to substitute time, which is t equals 3 seconds, to get the velocity at time t
E.
equals 3 seconds. Now if you use this relation ds by dt, you can write this relation as ds equals p dt, and when you integrate it, you can actually get the position expression as a function of time, like here. So you use this relation v equal ds by dt, you integrate this expression, and you got an expression which is a function of time. So at time t equals 3, you actually get the position. And
Okay.
if
So
you
these are
hmm,
basic maths, right? It's not
yeah, yeah, so
it's very general. It's not something specific
yeah,
anyway.
so in most of the question we use the same concept. Like here, the acceleration was given as a function of velocity, like acceleration was minus 0.4 v cube. So you again use the same similar concept, like those two formula, v equal ds by dt and a equals dv by dt. By using these two formula, you can actually get velocity and position.
Got it.
So most
So
of the
this I
problems
think
were like
this
this.
I can understand. I don't think this should be complicated. But after that, it might get difficult. I don't know. I'll try.
Yeah,
But like 2 weeks is enough time, right? Like if I
yeah,
study
yeah,
every day for a few hours, it should be enough, right?
yes, yes,
Okay. Thank you much.
yeah. Then in the fifth question, we use the same concept, but the only difference was now this position is a vector, it's a displacement vector. So the velocity vector is now given as the rate of change of displacement vector, and acceleration is the rate of change of velocity vector. And here later then we see that how the distance and displacement different to each other. So this distance is a scalar quantity, so and this displacement is a vector quantity. So we found that, so it was, so this was a question where this car actually moved from point A to point B, and then point B to point C, and we need to find the distance and displacement for the case. So the distance is pretty simple to find. So first you need, because it's a scalar quantity, you can use the additive property of a scalar, that
Ye-
from A to B it's 2 kilometer, and from B to C it's 3 kilometer. So total distance will be 2 plus 3, 5 kilometer. But
Yes.
the displacement, where you cannot do this. To calculate the displacement, it actually depends on the initial position to the final position. So you can see the initial position is A and the final position is C. So the displacement is a vector quantity which has the form of x in the horizontal direction and y magnitude of y in the vertical direction. So at point C you have to see what is the magnitude of x and y. So the magnitude of x is 2 kilometer in the positive x direction, so it is 2I, and this is 3 kilometer in the minus y direction, in the downward direction,
Those are
minus,
unit vectors, right? I and G.
yeah, so it is 2I minus 3j. So this will be your displacement vector.
So that is the answer.
Yeah, so that is the answer.
Okay, so there is no numerical answer as such. We can just write.
Yeah, because displacement is a vector quantity, so you will get an answer in the vector quantity itself.
Uh, there should be some mathematical thing, no, just to convert it to a final. Like, see, A to C would be a straight line, so that is some value. Any, okay, we can just do the uh, Pythagoras theorem there. But I'm just saying, like, just the uh, two square plus three square. So
No, that usually occur in the scalar problem, like in the previous problem we have. So in the previous problem we have actually the component of Vx, component of Vy. So this will be dx by dt and this will be dy by dt. So you can actually get the scalar answer like 2 meter per second or some 3 meter per second. But when you are dealing with the vector quantities, you will get an answer in the vector quantity. So for example, like in this problem also, there are
no,
yeah.
like if someone has to make sense of that final answer, 2i plus 3j, what would it mean? Like 2 in the x direction, 3 in the
Yeah, yes,
negative y.
yes,
Is that how I should be
yes.
okay saying it?
So for example, in this problem, we need to find the displacement vector. So we need to find the displacement vector RAB, which is from point A to point B, and RAC, which is point A to point C. So in the displacement vector, the initial and final location matters. So for RAC, my initial is A, final is C. So you can see in this plot that my x is this diameter, which is 40, and my y is 0. So my RAC will be 40i, and for B my x is 20 and y is 20, so it will be 20i plus 20j. So if you take calculate the velocity between AB, velocity between AB, so it's a vector, so it will be RAB divided by time. So it will be d by dt 20i plus 20j.
And how do you solve it? I like how do you even differentiate
So
20i?
this delta t is was given, which is 1 second. So it takes 1 second to go from A to B. So this will be 20i plus 20j divided by 1. So the velocity will become 20i plus
That
20j.
answer will be in vector notation only then.
Yeah, so this
I
will be the velocity vector 20i plus 20j. If you want to calculate the magnitude, as we have discussed in the previous problem, then it will be vx square plus vy square. So this will be 20 square plus 20 square. So this will be 800 under root. So this will be the overall magnitude of this velocity. But in the vector form, this will be the answer. If you've been asked to calculate the magnitude, then root 800 will be the answer.
So for the previous question also it's the same, right? Like
Yes,
root
yes.
of 2 square plus 3 square and 5 would be the answer.
Yeah, so this expression is for the general vector case. So any vector will have a magnitude of this. So if
So,
this is my vector, then it will have the magnitude of x square plus y square under root.
okay. No matter how the points are shaped, like it should not be a right angle triangle, right? Like
No, no, because it's a magnitude is a scalar quantity, so it doesn't matter what is the direction of anything. So it will always be a root 800
so,
multiplied
the
by.
classes that have been mentioned in the course syllabus that should be enough, right? Like for the exams, it should
Yeah,
not
yeah,
be
it should be enough.
too much. Okay, I'm a little worried about these sections. I've never done this. So,
You
like,
can have a book, uh, Merriam and Craig. So this is the book you may easily find. You can find the PDF of this book.
I have a Ferdinand beer right now.
Yeah,
So it may have some things out of it, but I'll see.
yeah,
Uh, but Himanshu, what I'm trying to tell is, see, textbooks right now maybe a little difficult to first to finish so many lectures. It's going to take a little bit of time, right? So after that, I don't think textbooks is possible within that timeline. Within I think 2 3 weeks the exam so is going to be there because the problems are going to take a lot of time. So textbook it might not be possible right now, but I'll do it after the exam just to go into the depth of it. But just to clear the exam, I'm a little worried if these lectures are going to be enough. And
Yeah, those will be enough.
right. Thank you. No complex concepts, right? Like which are too difficult.
No, no. So few complex question we can solve, but that is only to understand the concept. But otherwise, in the assignment and in the exam, I don't think they will give very complex question.
Okay. Thank you.
So in the previous lecture, we have solved problem based on these equations where we have to find the velocity and acceleration. Given that we have a position vector and velocity vector, and most of these vector are defined in the Cartesian coordinate, and also these are valid for the translation motion. But now we will actually study the rotational motion. So the form of the equation will be the same. For example, my angular velocity omega will be given as d theta by dt, which is theta dot, and angular acceleration will be d omega by dt, which is omega dot. This can also be given as d squared theta by dt square, which is theta double dot. And let's say if you have a rotation about a fixed axis, so this is your fixed point, this is point A, which is rotating about O, having angular velocity omega,
What
and
is the second equation? The alpha is equal to. Is it the alpha symbol?
yeah, this is alpha, this is the angular acceleration, which is rate of change of angular velocity.
So okay, W is angular velocity. Alpha is angular acceleration.
Yeah.
Thank you. Acceleration.
So this is your angular acceleration, the normal direction, which is r omega square. This we have seen in the previous class and also in the beginning lecture when we were discussing about the curvy linear coordinate. And this is alpha t, which is r alpha. So this is a tangential and this is a normal component of alpha. This you can write also as v square by r or v omega and so on. And my velocity will be r omega. So these are the formula that we required to solve the problem. So these formula are in the scalar form. You can write this formula in the vector form also. So for example, my velocity is given as r omega. In the vector form, it will be omega cross r. My angular, so let me write this a n. So my at will be alpha cross r. My an will be, so this is r omega square in the scalar form. The vector form, it can be written as omega cross r. So you can see that if you convert this in the scalar form, this will be omega r. So this will be omega square r. If you convert this into the scalar form, it will be alpha r, and if you convert this into the scalar form, it will be omega r. So this is the same expression you will be getting here. So this is the vector form, and this is the scalar form of the equation. Now you can also, there might be a problem where you have given 2 points and 2 points have a different relative motion with respect to each other. For example, let's say you have a point B here and A here, and you need to find uh, the velocity or the position of vector A related to the vector B. Sorry, position motion and the position of point A relative to a point B, and this both point B and A have a different motion. For example, let's say if B and A is translating, so this is and it reached to B dash and A dash. Then at point B dash, I'm rotating this thing with angular velocity omega, so it will have A double dash. So there are two motion. First there is a translation from AB to B, A dash B dash. Then there is a rotation motion about a fixed point B dash, such that my A dash is now rotated to A double dash. So this is my R related B related to A, and this is my delta R B and delta R A. So you can see that my displacement vector RA first equals to displacement vector of RB, because both have the same displacement. But then I also rotated this from a point B dash, and it has the additional displacement RB with respect to A. So this is my equation of displacement of RA, and it is given as a displacement of RB plus relative displacement of point A with respect to B, which is RB dash A. Now if I take the time derivative, I will have VA equals to VB plus the relative velocity of point A with respect to B. And this relative velocity can be given as from the above relation that we have seen here, because it is rotating here, and the rotational, it is rotating with an angular velocity omega, so this can be given as omega cross r, which is this relation. So my VA equals to VB plus omega cross r. So this is the expression when you have 2 points and those 2 points are moving, and you are actually studying the velocity of one point with respect to the other point. So this is the one expression if you have a 2 point, and these are the expression if you have a single point. So we are going to use these equations to solve the problem. So let's solve first problem. Can you switch off the mic? Actually, your background is.
Sorry.
So in this problem we have the mechanism is used to convert the constant circular motion omega of rod AB into a translating motion of rod CD and the attached vertical slot. Determine the velocity and acceleration of CD for any angle theta of AB. So basically, when this AB rod is rotating with an angular velocity omega, there is a translation motion which is occurring at CD. So it is actually going back and forth motion, and this is due to the rotational motion of AB. So we have given the rotational motion of AB, we have also given the theta, we have given the length of the rod AB, which is L, and we need to calculate the velocity and acceleration of this translating motion occur by CD. So here you can see that you have given theta here and you have given this length. So basically you can actually calculate x. So if you have x, you can take the time derivative to get x dot, and then you can take again the time derivative to get x double dot. So this x dot will give you the velocity of this motion which is occurred by CD, and x double dot will be the acceleration due to this bar CD. So we have to find x and take the time derivative of x to find the velocity of CD, and again the time derivative of x to find the acceleration of CD. So we already know AB, which is L, we already have theta, so x can be given as L cos theta. So if I take the time derivative, I will have x dot minus L sine theta, theta dot. So this is my velocity of CD, and if I take the double derivative, then I will have minus L sine theta, so this will be theta dot, sine theta, theta double dot plus cos theta, theta dot square. So from the just before the question we have seen that omega can be given as d theta by dt, which is theta dot. So this quantity is omega, and this quantity is angular acceleration. So angular acceleration was theta double dot. So my x dot is minus L omega sine theta, and x double dot will be minus L sine theta alpha plus cos theta omega square.
Uh, why did cos omega square?
Because this theta dot is omega, so theta dot square will be omega square. And this theta dot will be omega, so you can substitute here theta dot, so this will become omega square.
Okay.
So it was a simple differentiate exercise of differentiating of x with respect to time, and you can see this was the pretty much same concept that we have used previously. For example, velocity, which is rate of change of displacement, and acceleration, which is rate of change of velocity. So here, in order to calculate the velocity and acceleration of CD, we need to have x. Once you get x, you take the time derivative of it, so it will be velocity of CD, and it will be L sine theta, theta dot. So your omega is theta dot, and your angular acceleration is theta double dot or omega dot. So you will get x dot as minus L sine theta, theta dot. So this theta dot will be omega. So it will become L omega sine theta. So this is the expression of velocity of CD. And when you again differentiate this quantity, you will get minus L sine theta, theta double dot, and theta double dot is alpha, and theta dot square will be omega. So this will be sine theta alpha plus cos theta omega square. So this will be the acceleration of CD. We can solve a similar problem here. So determine the velocity and acceleration of the follower rod CD as a function of theta when the contact between the cam and the follower is along the straight region AB on the face of the cam, and the cam rotates with a constant counterclockwise angular velocity omega. So it's a similar problem. So we need to determine the motion of CD, velocity and acceleration of CD. So as this rotated, what happened? The CD tried to go in the backward direction. Okay, so let me define this quantity xc. So this is r. So I will have a triangle here. This is 90. This is theta. This is r. So based on this, I will have, so if my xc changes, my xc will increase, then this CD will go in the backward direction, because you can imagine, because if it is rotating in this direction, counterclockwise direction, this is going in the backward direction, and if it is rotating in the clockwise direction, then what happens, this CD will move in the right hand side direction. So it's all depend on this magnitude of XC, the rate of change of XC in time. So this axis keep changing, this axis keep changing in time, because based on this rotation this axis is either increasing or decreasing in time. And we know that the rate of change of XC will give us the velocity of this motion CD, and rate of change of, if we do the double differentiation, then the d square XC by dt square will give me the acceleration of the CD. So first we need to identify XC, take the time derivative of XC to find the velocity of CD, then again take the time derivative to find the acceleration of CD, because it will be like this. So this is my cam and this is CD. Now if it is rotated like this, so it will become in the backward direction, and if it is rotating like this, it will be more in the right hand side direction. So this CD will keep oscillating in the x direction, and we need to find the velocity of this oscillation and acceleration of this oscillation in the x direction. So again we have identified the right angle triangle here. We have given r and we have given theta. So from the property of triangle we can write down the xc, which is r by cos theta, or r sec theta. Then if you differentiate this quantity in time, you will get r sec theta tan theta theta dot, and again my angular velocity will be theta dot, my angular acceleration will be theta double dot. So this theta dot is my angular velocity of this. So x dot will be r omega sec theta tan theta. So this is my velocity of CD. So if you again take a time derivative of this, you will get x double dot c equals r, so it will be sec theta tan theta theta double dot plus theta dot. So now I am taking the time derivative of tan theta, so it will be sec theta sec square theta theta dot plus, now I will take the time derivative of sec theta, so it will be tan theta sec theta tan theta theta dot. So this theta double dot will be angular acceleration and theta dot will be the angular velocity. So my x double dot, which is the acceleration of CD, will be sec theta tan theta alpha plus omega, this will be sec cube theta omega plus sec theta tan square theta omega. So if you simplify this expression, you will have omega square plus sec theta tan square theta omega square. So this is the acceleration for x double dot. So again you can see, based on the rotational motion of this, you can able to find the velocity and acceleration of, translating velocity and acceleration of CD. Like in the previous problem also, based on the rotation of this, you can able to find the translation velocity and acceleration of CD. And the key idea is to actually calculate the XC in both of the question. Because this XC is not a constant, it is actually changing in time, because as this is going down or going up, this xc is either increasing or decreasing in time. So how xc is changing in time, it is actually creating this motion which is exhibiting translation motion in the x direction based on this xc. So basically, when you are finding the velocity of CD or acceleration of CD, basically you are finding the velocity of x and acceleration of x, because this x is changing, is a function of time, and when you take the time derivative of f, you will have the velocity, which is the time derivative of x, and the acceleration, which is the double derivative of x with respect to time. And the same thing we have seen here also, because this rate of change of xc is equal to the velocity of CD, because how the xc is changing, this is equal to how this CD is changing, and therefore this x dot CD will be the velocity of CD, and x double dot c will be the acceleration of CD. And you have already have x from this triangle, property of triangle, you can already calculate x as r sec theta. You just need to take a time derivative of this. So any doubt until now?
No, much.
So let's see one more similar problem. So here the block moves to the left with a constant velocity v0. Determine the angular velocity and angular acceleration of the bar as a function of theta. So as you can see, as this block is moving in the left direction, it will rotate, and we need to find that rotation, angular velocity and angular acceleration of this rotation. So it is a opposite problem that what we have seen. So in the previous problems, what happens that the rotation is creating the translation motion. So when any bar was rotating, this is translating, and we need to find the motion of velocity and acceleration of this translation motion, which is v and a. But now this is, here it is opposite, so it is translating, and this translation of the block is creating the angular motion of this bar. So as this move in the left hand side, you can imagine, for example, let's say this is my bar. As it is going, it is actually rotating like this. So it is going in the left side direction, and this bar is actually rotating in the counterclockwise direction as this block moves to the left hand side direction. So the translation of this bar creating the angular motion of this rod. So in the previous problem, the angular motion result in the translation motion. Here the translation motion results in the angular motion. So in the previous problem, we have given omega, and we need to find the translation motion like velocity and acceleration. Here we have given the velocity, and we need to find the angular motion, which is omega, and the angular acceleration of this bar. So just like before, you can see that you have given this x, and this is a, this is a, this is x, and you can see as the bar is moving in the left hand side, this x is changing, x is actually decreasing, and when x is decreasing, this is rotating in the counterclockwise direction. So this rotation is depend on the velocity of x and acceleration of x. So first, from the trigonometry of this triangle, we have theta, we have x, and we have a. We can write x as a by tan theta, which is a cot theta. So if you want to see how this x is changing, because this bar is moving in the left hand side direction, so as it is moving in the left hand side direction, x is decreasing. So we have non-zero rate of change of x in time, because because x is changing, x is decreasing. So this can be given by x dot. Basically we need to do the time derivative of a cot theta, so it will be minus a.
That constant velocity is indicated as v naught or v0.
This is v naught.
V naught. Okay.
So this x dot will be a cos sec square theta multiplied by theta dot, and we know that omega will be theta dot here, and this x, so you can see this v naught is in the left hand side direction. So this is my x, this is minus x, this is y, this is minus y. So v naught is toward minus x. So this x dot is minus v naught, right? So minus v naught will be minus a cos sec square theta dot, and theta dot I can write as omega. So v naught equals a cos sec square theta omega. So my omega will be v naught a cos sec square theta. So this will be my angular velocity of the rod. Now my angular acceleration is theta double dot or omega dot. So basically if I take a time derivative of this expression omega, I have omega, if I take a time derivative of this expression I will get alpha dot. So alpha will be d omega by dt. So this will be d by dt v naught a cos sec square theta. So you can see this v naught is a constant, v naught is not changing, so I can pull out v naught and a outside. So this will be v naught by a d by dt 1 by cos sec square theta. So my alpha will be v naught by a d by dt sine square theta. So 1 by cos sec square theta will be sine square theta. So if I do the time derivative of this, it will be v naught by a 2 sine theta cos theta dot. So this theta dot is omega. And my omega is v naught a by cos x square. So this will be sine theta cos theta v naught by a 1 by cos x square theta. So my angular acceleration will be 2 v naught by a square sine theta cos theta by cos x square theta. So this will be my angular acceleration and this will be my angular velocity. So it came by same approach, basically to identify x here, because x is changing as this block is moving to the left side direction. X is changing. Now how x is changing, that we will get when we take the derivative of this with respect to time. So when we do that, we will get x dot, which is minus a cos x square theta multiplied by omega, and this velocity is basically v naught, because it is said that block is moving in the with a velocity v naught. So this should be equal to the x dot, because x is changing in the same manner. X dot is x is changing in the same manner as how with the same velocity as v naught. So my v naught will be dx by dt. So x dot is v naught, it's a minus because my v naught is in the minus, it has a minus sign because it is moving in the minus x direction. So x dot will be the minus v naught, and this minus v naught will be minus a cos x square theta omega. So from this expression you can write down the expression of omega, which is v naught by a cos x square theta. So now to find the angular acceleration, either you can take a double derivative or again the derivative of this expression. So here you will get x double dot. So anyhow, so either you can take the again the time derivative of this expression, or you can take, or you can use the fact that alpha is omega dot. So you already have omega, which is v naught by a cosec square theta. So either you can take the time derivative of this or the time derivative of this. So this will give you x double dot, and x double dot will be equal to alpha. Or you can take the time derivative of this, so it will directly give you omega dot, which is alpha. So when you do that, you will get alpha, which was 2v naught by a sine theta cos theta divided by cosec square theta. So this will be your expression of alpha and omega.
How did you remember the answer?
No, I have written the answer, right? So I calculated it. I have written twice, so I remember.
V square by a square. The constant cosec square.
So until now we have looked a problem where we determine the angular motion or the translation motion, given that we have already given one kind of a motion and we need to find the another kind of a motion. Now we will solve the problem where we have a 2 points and we need to find the velocity of a one point based on the other points. Like in the beginning of this tutorial, we have used the relation where the velocity of point A can be given as the velocity of B plus the relative velocity of A with respect to B. So basically now we will be going to use this relation and see how we can use this relation into the problems. So let's solve this one. So here, if h and theta are known, the speed of A and B is v. Determine the angular velocity omega of the body and the direction of phi of vb. So basically we will be determining the angular velocity of omega here. So you can see there are 2 points now, A and B, and both points are moving with respect to each other. The motion of point A and B are also different. They are in the different direction. Even though they are the magnitude of velocity is same, they are of different directions, so the motion is different. And here we need to determine the angular velocity omega. So using the fact that Vb equal to Va plus relative velocity of point B with respect to A, and in the beginning of this tutorial we saw that the relative velocity given as omega cross r. So omega is the angular velocity vector and r is the displacement vector. So first we need to figure out the omega velocity vector and the displacement vector. So you can see the displacement is this. The distance between B and A can be defined by h. So my displacement vector is given by minus hj. So this is x, this is y, this is minus y, this is minus x. So this is minus h in the j, in the y direction, whereas you can see the angular velocity is in the clockwise direction. So the direction of angular velocity will be outside of the screen. So it will be omega equals omega in the z direction. This clockwise, let me assume clockwise is negative. So similarly we can actually determine Vb and Va vector. So my Vb vector can be given as, so you can see there is an angle phi here. So this can be written as minus V cos phi in the x direction plus v sine phi in the j direction. Just a minute. Yeah, so basically I'm taking the component of VB, because VB can be written as V, and based on the angle, this is my x component and this will be my y component. So my x component is in the negative direction, so this will be minus V cos phi, and y component is in the positive direction, in the positive y, which is V sin phi. Similarly my VA vector, you can see here, this is angle theta, so I need to calculate x component and y component to write in the form of vector. So in the x component it will be V cos theta, and in the y component it is V sin theta. So if I use this relation, now I can use equation 1 and write all the quantities in the vector form. So VB equals VA plus omega cross R. So VB is minus V cos phi plus V sin phi equals V cos theta plus V sin theta. And what is omega? Omega is minus omega in the z direction. So it is minus omega in the z direction, cross product with displacement vector, which is minus hj, minus h in the y direction, minus hj. So you can now suspect that this quantity, you are actually taking the cross product of k into j. So what will be the direction? When you take the cross product of k or j, you will get the direction I. If you take the cross product of I and j, you will get k. If you take the cross product of I and k, you will get the direction of j. So if you take the cross product of k and j, you will get the direction I. So this quantity is in the I direction. And what will be the magnitude? Magnitude is just a multiplication of this. So magnitude will be omega h. So this will be the magnitude and this will be the direction I. Basically it is minus I here. This is also minus. So I can write this as omega h I. So this is the property of a cross product. It's not related to mechanics, it's related to the mathematics, and it is a property of cross product. So now you have a quantity here, x component, here this is y component, this is x component, this is y component, and this is your x component. So now you can, from this equation, you can actually write two equations. One is in the x component and one is in the y component. So when you collect x component here, you can write v cos phi equals v cos theta minus omega h. So this is our equation 2. This is x component equation. And then you can write another equation in the y component, which is v sin phi equals v cos theta. This is equation 3, which is your y component equation. So basically you are writing the same equation. You are writing the same equation. So this equation written in the vector form. So you are writing now in the component form. So this is your x component and this is your y component. So you have these two equations. Sorry, this is sine, right? So from equation 3 you can see that sine phi equals sine theta, which will give you phi equal theta. and you can use this equation in equation 2. So it will be v cos phi minus omega h, or you can write in terms of theta here because both are same. So this will be v cos theta minus v cos theta equals minus omega h. So this is 2v cos theta equals minus omega h. Both will become positive, so omega will be 2v cos theta by h. So this will be your omega. So just to recap here, whenever you have given 2 points, 2 different points having 2 different motion, you have to use this equation where you need to determine the velocity of one point related to the other. So this is the velocity of point B, this is the velocity of point A, and this is the relative velocity which is given by this expression omega cross r. So your first job will be to determine all these vectors omega, r. So r will be this, it is given h here, and h is in the y direction, so it will be minus h in the y direction. Omega will be minus omega in the z direction, because you can see if it is rotating here on the paper, on the screen, then the direction is outward to the screen, which is the z direction. And from the figure we identify the vector vb and va. Now what we did, we substitute all the vector in this equation and we write down the big vector equation. Now it has both component, x component and y component. So we club x component together and y component together. So basically we got two equation, two scalar equation we got, and we solve this two scalar equation with each other to determine the omega. So let's solve one more this kind of a problem in order to get more clear on this. So here, if the block at C is moving downward at 4 feet per second, determine the angular velocity of bar AB at an instant shown. So again, here we have to use the similar concept that V1 equals to V2 plus the relative velocity. Because this point is moving, this point is translating with some velocity, and this point also translating, right? As this point is moving, this point is also translating. It is rotating and translating. It is doing both kind of a motion. You can see here it is rotating, and due to C, as C is moving upward or downward, this is also moving upward or downward, right? So this 1 can be C and 2 can be B, right? So you can use this relation here, because now still you have 2 points C and B, right? You have 2 points C and B, so you can use this relation where you define the velocity of point C, and it can be written as velocity of B plus the relative velocity between B and C. So once you determine the relative velocity of VB, we know that V can be written down as omega r as a scalar, or in the vector form it can be written as omega cross r. So once you get VB, you can get the omega, this omega AB into r. You can actually find the omega from the known velocity VB. So again we are using the same expression, VC equals VB plus the relative velocity between C and B. So this relative velocity between C and B will be omega CB cross R CB. So this is omega CB because this is also rotating. So now we need to determine RCB. So we have given an angle 30. So from this we can actually determine. So this is 3 feet. This length is 3 feet, and we have given an angle, so we can actually determine this magnitude and this magnitude. Once we get this and this magnitude, we can write RCB as xi plus yj, and this will be our displacement vector. So my x will be 3 cos 30 I plus 3 sin 30 j. So this will be 2.598 I plus 1.5 j. And we don't know about omega CB. We have not given anything in the question about omega CB. We only know that omega CB had some magnitude, let's say omega CB, and it is in the kth direction. It should be in the kth direction. That's the only thing we know. We don't know what is omega CB. We don't know what is omega AB also. This is the thing we need to find out. This is the objective, omega AB. So VC we know. VC is minus 4 in the jth direction. You can see here it's 4 feet. It is going downward, which means minus 4j. So this is the velocity vector at point C. In VB, we can use this relation for VB, omega AB in cross R. So VB can be written as omega AB cross R. This is RAB, and you can see RAB is 2 feet in the x-axis. So RAB is 2I. So now you have all the vectors. So you have VC, you have VB, and you have this vector also. So, so now you have substituted all the vectors in this equation 1, let's say. So you will have VC is minus 4j and VB is omega AB cross RAB. RAB is 2I. So this omega AB should also be in the k direction. So it is omega AB k cross RAB, which is 2I. This is our VB, and plus omega CB in k direction, cross product with RCB. This is RCB vector, so it is 2.598 I plus 1.5 j. This is omega CB cross RCB. So now you can see that it's cross product of k component with ith component. So this will give you jth component, minus jth component, and the magnitude will be 2 multiplied by omega AB. So this quantity is in the minus j the direction. So it is 4j minus 2 omega AB j. Similarly, if you take a cross product between k into I, you will get something in j. If you take a cross product between k into j, it will give you in the direction minus I. So if you take the cross product between this and this will be in the j direction. If you take a cross product between k and j, it will give you in the minus I direction. So this will be 2.598 omega CB j minus 1.5 omega cb in I direction. So now this is our vector equation we got, and as usual we will take the component of it, right? So we will take, let's say we will take ith component, x component, so it will be 0 equals minus 1.5 omega cb. This is the x component. So from this you can see omega cb will be 0 from this equation. If you take y component, you will have minus 4 equals minus 2 omega AB plus 2.598 omega CB, and this term is in x component, so you need to write here. And from x component you see that omega CB is 0, so this will be 0, omega CB is 0, so you will have 4 equal to omega AB, so omega AB will be 2 rad per second. So you get the angular velocity of AB. So we didn't knew the angular velocity of CB also, but from the x component equation we saw that it's 0. Then we solved y component equation and we saw that our omega AB is come out to be 2 rad per second. So just to recap here, we use the fact that there are multiple points which are connected to each other, and if one point, let's say C, is moving, the other point B is also moving somewhere, having some translation velocity, and when this happens we have to use this equation, Vc equals Vp plus relative velocity between them. So the major thing is to identify all the vectors. For example, Vcb can be given as omega Cb cross Rcb, so you need to identify Rcb here. So for that we identify this as 2.5 in the x direction, 1.5 in the j direction. Then you need to identify this. So the angular velocity always in the k direction, in the z direction. So once we figure out all the vectors, we actually got this equation on substituting all the vector in this equation. We got this equation, and then as like we did in the previous problem, we pull out x component and y component equation. So x component equation give that omega cb is 0, and y component give us the answer, that is omega AB is 2 rad per second. So in the previous problem also we did the same thing. We got 2 points, both are moving in the related to each other, have different motion. Use the same formula, and first we figure out all the vectors like VB, VA, the displacement vector. We substitute all the vectors here. Then we pull out x component and y component. The x component gave us that theta equals to phi, and y component gave us the answer omega. Here also we did the same thing. We write down the same formula between B and C, identify all the vectors, position vector, velocity vector, angular velocity vector, substitute into the equation. We got full vector equation, pull out x component and y component. X component gives us omega CB 0, and y component gives that omega AB is 2, which is the answer. So any doubt in this problem?
No much.
So again we will solve a similar problem only. So here, if the flywheel is rotating with an angular velocity of omega A 6 rad per second, determine the angular velocity of rod BC at instant shown. So this flywheel is rotating with an angular velocity VA. So if I use the same formula between point B and C, such that my VB equals to VC plus relative velocity between two, and my relative velocity between two will be omega VC cross displacement or displacement vector at BC. So in order to use this formula, first we need to identify all the vector VB, VC and this omega BC and RBC. So VB is this. So we have already given omega A, and we know that V can be written as omega R. In the vector form it is omega cross R. So if we have given omega here, which is 6 rad, and this is the radius 0.3, then this velocity will be, this is omega R, so this is 0.3 multiplied by 6, so this velocity will be 1.8. The magnitude will be 1.8, but we need to define a vector. So this is my magnitude of point P, but we need to define the vector of VB. We don't need a magnitude, we also need direction. So for that we will not use this scalar formula, we will be using vector formula. So it is omega, which is 6k, it is in the clockwise direction, so it's minus 6k cross product with RB, which is 0.3j. So this is minus 1.8 I meter per second. So this is my velocity vector at point P. Similarly, I can find the velocity vector at C, because this is also rotating. So my VC will be omega CD cross RCD, right? I am using the same formula which I have used to calculate VB. So I don't know what is omega CD, but it is in the k direction. Cross product with RCD, and RCD I can find because this is 0.6 and this is 60 degree. So my RCD will be 0.6 cos 60 in the ith direction plus 0.6 sin 60 in the jth direction. So my VC will be omega CD 0.6 cos 60I plus 0.6 sin 60j. So this will be my omega CD vector. I mean, you can further simplify this. When you take the cross product between k and I, you will get something in j, and when you do between k and j, you will get in minus I. And the magnitude is very easy, you just need to multiply it. So it will be 0.6 cos 60 omega CD, and this will be 0.6 sin 60 omega CD. So this VC will become in the jth direction minus 0.6 sin 60, this is omega CD, in the ith direction. So this is your vector of VCD. You have VCD vector, sorry, velocity VC vector, you have velocity VB vector. Now you need to calculate this expression, omega BC cross product with RBC. So we don't know this, and this is the goal of this problem. We need to find omega BC, and RBC we can find very easily because it is 1.5 meter, and it is given in that we need to determine the angular velocity at a given instant. So at this instant it is 1.5 meter in the x direction. So this RBC is just 1.5 in the ith direction. It's minus because it's a minus x-axis, minus 1.5 I. So this is this thing. So now we substitute all the vectors in equation 1. So VB is minus 1.8 I equals VC, which is omega 6 cos 60 omega CD in the j, 0.6 sin 60 omega CD in I, plus omega AB cross product with minus 1.5 I. and this is in kth direction. So this k multiply k cross product with I will give you direction j with a magnitude of 1.5 multiplied by omega AB j. So this is the vector, and now the same thing, we need to pull out x component and y component. So if you pull out x component, you will have minus 1.8 equals minus 0.6 sine 60 omega CD. So here you will find omega CD as 1.8.6 sine 60. So this will be 3.529 rad per second. And when you pull out y component, so this is y component and this is y component. So this will be 0 equals 0.6 cos 60 omega CD minus 1.5 omega AD. So omega CD we know, which is 3.529. 0.6 cos 60 3.529 minus 1.5 omega AD. So this will be 1.058 divided by 1.5 omega AD. So this will be 0.7 rad per second. So here you find both omega AD, which is 0.7, and omega CD, which is 3.529 rad per second. And we have used the same expression here. So the only difference in this question is, in this question you don't have directly given this point VB velocity and VC velocity. If you don't given any translation velocity VB and VC, you can always use this formula to calculate. So for VB we use this formula because we have already given omega A. So from this we actually got VB. For VC we use the same. We use the omega of this omega CD cross product with this displacement. So we got the VC vector also. In the previous question we have solved here. We have directly given this VB, VC and VA. So we just directly identify the vector and substituted in this formula. But here we have not given VB, VC directly. So we use the fact that V equals omega R in the scalar form and omega cross R in the vector form. We have already given omega A, so we can easily form VB. Here VC can be written as omega CD cross product with this displacement vector. Then the relative velocity can be given as omega BC cross with R BC, because this is the relative velocity of B with respect to C, and it is also moving with some angular velocity. So we identify RBC, which is very easy because it's 1.5 meter in the x direction, so it is 1.5 I. And omega BC we need to find. So basically we need to find two angular velocity here, angular velocity of CD and angular velocity of AB. And we write down the equation in the vector form here using this equation 1, and from that you can easily get two equations. One is x component and one is in y component, and in both of this equation you find different omega. In x component you found omega CD, and when you use y component you found omega AD. So any doubt in this question?
No much.
Now we will solve very easy version of this. So this is the question. Whatever we have done now, it's a pretty much easy version of this. So here the pinion gear A rolls on a fixed gear rack B with an angular velocity omega. Determine the velocity of the gear rack C. So we need to find the velocity of this point C, and this is the another point B. So again we can use the same relation, Vc equals Vb plus relative velocity between them. So Vc equals Vb, and this will be omega Cb cross product with displacement of Cb. Now what is omega Cb that we have given, which is 4 rad per second, because this should be the omega cd, sorry, Cb, and this part is rotating with omega, so this is 4 in the z direction. And what is displacement RCB? Basically this displacement of RCB, which is the diameter of this gear, and this is 0.3 in the jth direction. So my Vc equals Vb, and Vb is fixed because it is written that it's at B this gear is fixed, only this gear is moving either in the left or right hand side direction. So if this is moving in the counterclockwise direction, this C will move in the left direction, so this will be minus Vc, and Vb will be 0, Vb vector will be 0. So this is 0, sorry, this is 0, so this will be omega Cb cross product with RCB. So Vc, this will be 4k cross product with 0.3 j, and you know that when you take the cross product of k and j, you will get minus I, and the scalar will be given as 4 multiplied by 0.3, which is 1.2. So my Vc vector will be minus 1.2 I. So this will be my answer. So the velocity, magnitude of the velocity is 1.2 meter per second, and minus, it is in the x direction, that too minus, which means it is actually moving left hand side direction in the x axis. So any doubt in this?
No, Himanshu.
So in this class we will be solving till this question only. So in the next class we will solve one or two more problems related to this same expression, and then we will move to the next topic, which is the instantaneous velocity. Basically in that concept we will be solving the same problem, but we will use more graphical approach. That's the only difference. And after that we will be moving to the next topic, which is momentum, impulse, and so on.
What is the schedule of the next class?
I think Wednesday same time.
They have not sent an email. I've seen.
I already sent them email about this. I think today is the holiday, that's why maybe they are not sent mail.
Okay. So Wednesday and after that again Saturday, normal.
Saturday I don't know if I can able to take, because I'm traveling on Saturday, so
Okay.
I will inform in the mail itself. I will mail them about. I have not decided when to take the Saturday class.
Okay. So right now Wednesday 7 to 9. Huh?
Yeah.
They have not sent the email yet. We,
Yeah. So the next class will be Wednesday 7 to 9, and then I think there is one class on Friday also, 7 to 9.
Friday. Okay.